Good morning, all. In the previous session, we have discussed about wavelength division multiplexing, that is WDM, and what is actually the WDM, what are the components and its features. Uh, in the WDM, there is an important thing is that the passive optical coupler, there are so many WDM components are there. One of the important types of components is the optical couplers. So passive optical couplers. Now we are going to discuss about the passive optical couplers. These passive devices operate completely in the optical domain that to split and combine light streams. These things are used to split or combine light streams. So in the multiplexing and demultiplexing stage, we can use it. They include N by N couplers with N greater than or equal to, that is 2 by 2 coupler is a basic coupler, and power splitter, power taps, and star couplers, etc. These type of couplers. Most passive WDM devices are the variation of the star coupler concept. All these things are the variation of the star coupler concepts. The star coupler concept is explained here. So we will discuss this thing in detail in the next session. Now, just please go through this diagram. That is, it's a basic star coupler concept of the combining or splitting optical power is shown here. They are the inputs of the different signal having the different power P1, P2, etc. That is Pn. And after the star coupling, we get the output signal. There are many output signal. The output from each port is equal to 1 by n of P1 plus P2 plus etc. is Pn. So here, which can perform both power combining and splitting. In the broadest application, star couplers combine the light stream from two or more fiber inputs and divide them among several output fibers. In the general case, the splitting is done uniformly for all wavelengths so that each of the n output receives 1 by n of the power entering the device. That is actually shown on this figure. So then first of all, we have to discuss about the 2 by 2, that is n by n, basically the 2 by 2 fiber coupler. A device with the two input and two output is that is called a 2 by 2 coupler. You can see in this figure, this is shown here a 2 by 2 coupler here. 2 by 2 coupler is a simple fundamental device that is fused fiber coupler. That is, you can see it's a fused fiber in the middle of this coupler. You can see that the fused fiber. So that's called, that is simple fundamental device that is fused fiber coupler. So this is fabricated by twisting together, melting, and putting two single mode fibers. You can see two single mode fibers. They are twisting and melting and fusing. And we can, after the fabrication of this coupler is together, melting and putting two single mode fibers. So they get fused together over a uniform section of length n. You can see in this figure over a length, there are different length is shown here. It is fused at a particular length. These two different single fibers are fused and melted, that is twisted, melted, and fused that to form. Each input and fiber has a long tapered section of the length L. You can see in this figure is a length L that is at the two end of the two end stage of this fused area. You can see that is tapered region, that is you having the length L, and the transverse dimensions are gradually reduced down to the coupling region when the fibers are pulled during the fusion process. The total draw length is L equal to 2L plus W. You can see from that figure, the total length is equal to W plus L plus L, that is 2L plus W. That's the total length of this. This device is known as fused biconical tapered coupler. And you can see the different input power of the power representation, represented denoted here. That is input power with the P0 and the throughput power P1 coupled to power P2 and the crosstalk P3. All these are noted here. You can see here, that is here P0 is the input and P1 is the throughput power. P2 is the power coupled into the second fiber, and P3 and P4 are the extremely low signal levels. And as the input light P0 propagates along the taper in fiber 1 and into the coupling region W, there is a significant decrease in V number, and reduction in the rates R by lambda, where R is a reduced fiber radius. As the signal enters the coupling region, an increasingly larger portion of the input field propagates outside the core of the fiber. Depending on the dimensioning of the coupling region, any desired fraction of this decoupled field can be recoupled to the other fiber. By making the tappers very gradual, only a negligible fraction of the incoming optical fiber is reflected back into the either of the input ports. So these devices are also known as directional coupler. That is, by making the tappers very gradual, only a negligible fraction of the incoming optical fiber that is reflected back to the either of the input ports. So these devices are known as directional couplers. So assuming that the coupler is lossless, then the expression for power P2 coupled from one fiber to another over an axial distance z, you can represent that is power P2 equal to, there is a expression for the power coupled from one fiber to another power fiber, that is P2 equal to P0 sine square k z. Z is an axial distance where k is a coupling coefficient. By conservation of the power for ideal core fibers have P1 equal to P0 minus P2. P0 minus P2, you can see from the figure. That is P0 minus P2, as we can substitute this P2, P0 into sine square Kz. So while taking the P0 is common, that P0 into 1 minus sine square Kz. And you know that 1 minus sine square theta is cos square theta. So you can substitute that here, P0 into cos square Kz. That's why we get the P1 equal to P0 cos square Z, the P2 equal to P0 sine square Kz. From these, we get the equation for P1 and P2. One is sin P0 sine square Kz and another one is P0 cos square Kz. That the phase of the driven fiber is always lags 90-degree behind the fiber of the driving fiber. So P1 is, I think, P1 is a as a input power, and P2 is the power coupled from one fiber to another fiber. From this equation, the phase of the driven fiber is always lags 90-degree behind the phase of the driving fiber, because the P2 equal to P0 sine square Kz, whereas P1 equal to P0 cos square Kz. Okay. And the percentage division of the optical power between the output ports by means of a parameter termed splitting ratio or the coupling ratio. The splitting ratio or the coupling ratio we can calculate it as P2 by P1 plus P2. P2, you know that P2 actually the power coupled from one fiber to another fiber, P1 is input power. And the two basic losses in regarding these practical fibers are excess loss and insertion loss. While we are calculating the excess loss, we can calculate this as 10 log P0 by P1 plus P2. P0 by P1 plus P2. And in case of insertion loss, that is the loss of a particular port to the port. That is, from input port I to output port J, we can calculate the insertion loss. That is 10 log Pi by Pj. So crosstalk or the return loss is a measure of the degree of isolation between the input at one port and output and optical power scattered or reflected back to the other input port. That is actually the crosstalk. So we can calculate this crosstalk, that is 10 log P3 by P0. Okay, these are the important equations. You may expect some numericals based on this equation in your exams. So let us see an example. That is a 2 by 2 by conical tapered fiber coupler has an input optical power level of P0, 200 microwatt, and the output power is at the other three ports, that is P1 equal to 90 microwatt and P2 equal to 85 microwatt and P3 equals 6.3 nanowatt. We have to determine this coupling ratio, excess loss, insertion loss, crosstalk, etc. So by using the equation of the coupling ratio, we can substitute, that is P2 divided by P1 plus P2, that is 85 by 90 plus 85, that into 100, that is 48.6 percentage you will get. And while substituting in the excess loss equation, that is 10 log P0 by P1 plus P2. Actually, P0 is 200 microwatt and P1 is 90 microwatt and P2 is 85 microwatt. You are substituting, you get the excess loss is equal to 0.58 dB. Okay. These are just a substitution of this equation. The insertion loss from particular port to another port. First, you calculate the insertion loss from port 0 to port 1. That time, the equation 10 log P0 by P1, that is port 0 to port 1. So 10 log 200 by 90, that is 3.47 dB. You will get. And if you are calculating the insertion loss between port 0 to port 2, then you are substituting the equation as 10 log P0 by P2, that is 200 by 85. 10 log 200 by 85, that is 3.72 dB. That is actually, and we can calculate the crosstalk by using the equation 10 log P3 by P0. That is P3 is 0.3 nanowatt divided by 200 microwatt. You will get that is minus 45 dB as the crosstalk. Okay, and another type of coupler is the star coupler. We have mentioned just in the initial stage. An N by N star coupler is more general form of the 2 by 2 coupler as shown in this figure. This figure already discussed briefly there. That is P1, P2, P1. They are the P1, P2, etc. Pn are the inputs, and there are the outputs. In the broadest application, star couplers combines the light streams from the two or more input fibers and divide them among the several output fibers. In the general case, the splitting is done uniformly for all wavelengths, so that each of the n output receives 1 by n of the power entering the device. That is, output from each port is 1 by n of P1 plus P2 plus etc. up to Pn. That is, we get the each of the n outputs receives 1 by n of the power entering the device. Then star splitting loss is an important thing here. And in an ideal star coupler, the optical power from any input is evenly divided among the output ports. The total loss of the devices consists of its splitting loss plus the excess loss in each path through the star. The splitting loss is given in the decibels by splitting loss equal to minus 10 log 1 by n. That is, this minus log 10 by log 1 by n we can return as 10 log n. The splitting log is actually 10 log n. Okay. And for a single input power P in and n output powers, the excess loss in decibel is given by fiber star excess loss, that is 10 log P in divided by sigma I equal to 1 to n P out I. The insertion loss and cross-check can be found from the previous equation as we mentioned in the 2 by 2 coupler also. Okay. These rings are the different passive components, passive optical components. They are used in the WDM. They are called as WDM components actually. Okay.